I have a feeling that I start every module with almost the same sentence, that we already had a look at a lot of algorithms and learned a lot of things about algorithms. And this is true. We really made a lot of progress. We had a look at a lot of different algorithms and a lot of different categories of algorithms. And the overarching goal of this course, of course, is to make sure that you don't learn as many algorithms as possible by heart, but that you get a feeling for how you may derive algorithms, for how you may think about algorithms, and for how you may judge algorithms with the big O notation. Now in this module, we're going to have a look at a different category of algorithms. We're going to have a look at algorithms on sets, which are roughly arrays. Sets are arrays, but I'll talk in more detail about what sets are exactly and what sets, no pun intended, them apart from regular arrays. Now you see the subtitle, Getting Tricky, because some of the algorithms we're going to have a look at right now will be a bit more difficult to come up with, but we'll be able to do it, of course, together in this module. So what's inside this module? Of course, first of all, I'll clarify what exactly sets are and what set algorithms are all about, and then we'll simply have a bunch of examples. Now, there are loads of algorithms that have to do with sets, with arrays, and the goal is not to cover them all, because the goal is not that you learn them all by heart, as I mentioned already. Instead, we'll just have a look at some examples so that you get more ideas of how to think about algorithms and how you might be able to solve them. So what are set algorithms all about, and why am I saying array in parentheses here? A set in programming, in mathematics in general, is basically a collection of values, for example, objects or numbers, but could also be text, which forms an entity on its own. And that's the important part. So we're talking about arrays where the array itself also can be treated as an entity. Now let me give you an example. Let's think about shirt manufacturing. You're owning a factory, a company that creates shirts, t-shirts, regular shirts, whatever. Now, when you're working on your new shirt, you might have different options for the colors of the shirt, and you might also plan to build certain or to produce certain sizes for the shirt. Now, both colors and sizes would be sets. We have different values in there. So in programming, we would represent it as an array, but the overall array in itself is a thing. We have that colors set, which then has different options, and we have the sizes set. So it's really just a way of naming things. And actually, most arrays, therefore, are sets because you rarely have arrays of random unconnected data, of course. So it's really just a term which you'll sometimes hear, and that's why you can typically translate it with array in programming, because most arrays are sets. You rarely have arrays of disconnected values. Now, relatively often in programming, we'll have to solve problems where sets are involved. Let's stick to this shirt manufacturing problem here. Let's say our goal is to come up with a program with an algorithm that gives us all the combinations that have to be produced. Now, of course, that's fairly simple for these two sets here, but of course we could be operating on bigger sets, and or we simply want to automate this task because we're not just producing one kind of shirt. So therefore we have to derive a new set which includes all the variants that should be manufactured. And in this example, this would be this set. We can have a blue shirt in M and L sizes, and the same for the red shirt. And again, for more options, of course, we would have a bigger set. And even if we only have always just two options in each set, we still might want an algorithm that does this for us, a program, a function, so that we can automate this because the input values, for example, the colors, might differ. And that would be one example for a set algorithm. This problem which we want to solve can be solved with an algorithm which we would call a set algorithm because it operates on sets, on arrays, and it actually also produces a new set here. And this specific algorithm would be the Cartesian product algorithm. Now let's see how it could look like in code. Let's write a program, a function that is able to basically multiply two arrays with each other and give us this new array where we have all the combinations as nested arrays. So back in our well-known starting setup here, I'm back in the app.js file, and I will add a new function, cart product, which does not stand for shopping cart, but for Cartesian product. And in a simple form, we could say that we always expect two sets, two arrays as inputs. So we have set A and set B, for example. And for a more specific algorithm, if we knew that we always operate on sizes and colors, we could of course also name this colors and sizes. But I'll write it a bit more generic and have set A and set B. Now, the goal is that when we call the Cartesian product algorithm, I'm able to feed in two sets and get this multiplied set as a result. So we might have our colors set, which is an array where we have blue and red. So let me add this. And then we might have our sizes here, where we have M and L. And my goal is that I'm able to feed those two sets in, and I get as a result, which I'm going to log here, basically a new array where we have nested arrays, and that would be blue and M and so on. So all the other nested arrays you saw on the slide before. That's the goal here. Now, how could this algorithm look like? How can we solve this problem? Well, of course, first of all, we can implement a check where we check if the inputs actually are empty or anything like that. But I'm going to omit this here. You might want to add it if you can't guarantee that you always get valid arrays. I do assume that I do get arrays, so therefore I will not check whether my two input arrays, my two input sets are empty or anything like that. And therefore, instead, what we want to do is we want to derive a new array here, right? So that's the ultimate goal. We have a new array full of nested arrays. Therefore, we can create our new array product, because it's the product of these two sets. And of course, we can't just say product is set A times set B. That's not a thing in JavaScript. You can't multiply arrays. And these two inputs will be arrays, of course, because we operate on sets, and sets, as I mentioned, are just arrays in programming. So this is not a thing in JavaScript. So therefore, we'll initialize this to an empty array, and we'll have to add items to that array. Now, how can we do that? We get two input arrays, and we need to multiply every element from the first array with the second array. Or not really multiply, I should maybe say we need to combine it. Now, what would make sense, therefore, is that we write a loop where we go through all the elements in the first array, and we have a nested loop in there where we then also go through all the elements in the second array, so that we have a look at all the elements in all the arrays, and then we combine that inside of the inner loop. So I have a loop here where I go through all the elements in the outer array. So set A, L for element of set A, for example. And in there I have a nested loop where I have my set B element of set B, where I go through all the elements in the second set. So we have a loop inside of a loop. Now here I then reach out to product, so to this empty array, and I push a new element onto it. And the element we push into that array itself is an array, because our goal is to have a bunch of nested arrays in that outer array in the end. And what goes into the nested array? Well, the element from set A, at which we're having a look in this outer loop, and then the element of set B for that inner loop. Because with those loops, we go through all elements in B for all elements in A. And therefore here we have set A, L, and set B, L. And that's the nested array we add to this product array. And that actually should be all. If we now return product here, we should be able to run this code and actually see this expected output, this expected array full of arrays as an output. So if we go to the browser and we run this, indeed we see we get an array full of arrays. And if I expand this, you see the arrays I have in there are nested arrays where we have blue and M, blue and L, red and M, and red and L. So that's exactly that Cartesian product which we wanted. And as a side note, you are not limited to just equally sized arrays. If we also had, let's say, S as a size here, so if one array had 3 elements and the other array had 2 elements, that would also work. If I now reload this, you see we still have a valid output. We just have more combinations, of course. So that's also important. We don't have to have the same sizes here. Now for the big O notation. What would be big O of this algorithm? Let's derive it in the next lecture. So what is our big O here? What's the time complexity of this algorithm? Now, this algorithm has one important limitation. We only have two input sets. Those sets can be of any size, and they don't have to be of the same size, but we don't have more than two sets as an input. That's important to keep in mind here. So what is our big O notation therefore here? What's our time complexity of this algorithm? We have a nested loop, and a nested loop often means that we have quadratic time complexity. However, that's not the case here, because quadratic time complexity really is only the case if our nested loop operates on one input value. For example, if we have one array, and for that same array we have a nested loop, as we had it, for example, in our sorting algorithms, in our bubble sort, for example. There we had a nested loop where we actually went through the same array twice. Then we had quadratic time. Now here we also have a nested loop, but we operate on two different arrays. And therefore, of course, we depend on two lengths, on two input values, on the length of the first array and the length of the second array. We can, of course, see this here. If I add a console log here in the middle, where I say running, and I save that and reload, you see running 6 times here. Now, if we had an input where, let's say, one array only has one element and the other array has two elements, you see this only runs twice. So this is clearly not quadratic time complexity, where we would have 2 at the power of 2, for example, or 3 at the power of 2, or anything like that. Instead, the actual big O we have here, or the actual time complexity we have here, should be O of n times m, maybe written like this, where n is the length of the first set and m is the length of the second set, because the length of both arrays matters here. And we simply run this code here in line 6, n times m times. In total, it executes n times m times. That's how often this code runs here, and that's our time complexity for this Cartesian product here. Now, what about space complexity? If we also want to analyze that, space complexity here, well, we have one array which we create here when the algorithm runs, but that, of course, is only created once. But then we also have something that grows with the input size. And that is the element we're adding to this array. We're adding a new element, a new nested array, to this overall array for every nested loop iteration. So for the space complexity, we actually have the same as for the time complexity. It's n times m. Why? Because we create one new array, one new value, which is stored permanently in the product array for the duration of the algorithm per combination of our two sets. So we have n times m execution steps, and in every step we create a new value. So of course we have the same space complexity. Now here's also one other way of how you could look at the time and space complexity in this example. And that is that you don't really want to have a look at different lengths of the two sets, but instead you say, I only care about the worst case. And for whatever reason, I don't want to analyze the exact length of the two arrays. So therefore, what we could do instead is we could say, well, we assume that the size of the longest array is the size of both arrays. So then we would only have one input, n, because we would assume that both arrays would be of the same size. So then we could also argue that we have big O of n times n, which of course is n squared. The same would then be true here for the space complexity. Now again, this is a simplification. This is only true if both arrays are of the same length, because then n and m would be exactly the same value. But if we don't know the lengths, if we don't know if they have different lengths, and we want to have a general thesis about the space and time complexity, we could actually argue for square time and square space complexity, because we assume that the length of the longest array is the length of all the input arrays, so of both input arrays. That's why you could also derive this space and time complexity if you wanted to. Now, if you do differentiate between the two lengths, it's simply the product of the two lengths. And this should be fairly intuitive. So that's the Cartesian product array, which operates on two sets and which actually also produces a new set here, a set full of manufacturing variants in this concrete example. So now that we derived how to build the Cartesian product of two sets, what about an unknown number of sets? In this example of 3 sets. But how would the algorithm look like if we would not just accept 2 arrays, 2 sets as inputs, but instead we want to be able to calculate the Cartesian product of any amount of sets? How would that look like? Well, back in our code, we have this function card product, which does operate on 2 sets. So now we need some form of generalizing this to work with any amount of sets. Now, you can certainly find a lot of different solutions, short and longer ones, but I would say, since we already have a solution for 2 sets, we actually only need one more building block to be able to work with any amount of sets. We need some loop that goes through all input sets, no matter how many we get, and we always just have a look at 2 at a time and build a new set on those 2 sets we had a look at, and take this new result set, kind of a temporary set we built, and combine that with the next set in line. Sounds complex? Well, it actually isn't. Back in this example here, let's say we now also have our styles array, our styles set, and in styles we have, let's say, the round neck and we have the V-neck shirt. And you could of course have more styles, and maybe also, just to spice it up, we add one extra size here. So we have 3 sets now, and this function only works with 2. Well, we can add a new function, which we'll then call card product in a second, and I'll name this Cartesian. The name, of course, is up to you. Now, this should take an unlimited amount of arguments, an unlimited amount of parameters, where every parameter should be a set. So we take an unlimited amount of arrays as an input to Cartesian. So we don't just have set A, set B, and set C, because that would again limit it to just 3 sets. I don't want to impose any limitations. And in JavaScript, we can do this with the rest parameters syntax. For that, we add 3 dots here in the parameter list, and then any name of our choice, like sets. And what JavaScript will do is, when we call this with, let's say, 3 arguments, or 4 arguments, or how many arguments you want, all those arguments will automatically be aggregated into one argument, into one parameter, which will then be an array of those values. So just to show you how this works, if we console log sets here, so this aggregated parameter, if I would call Cartesian here with my colors, sizes, and styles, so with these 3 arrays I created up there, if I would call that and save that and reload, you see this output here from line 14, this is from this console log here, this is now an array full of those parameter values, so full of those arrays I passed as arguments. So that's how this rest parameters syntax works. So this is good because now we have a function that takes as many arguments as we want, and we get them all summed up into one array. Now we need to calculate the Cartesian product of those arrays in that array, so of those elements in that summed up array we have here. Now we do have card product, which works on 2 sets, but here of course we have more. Well, the implementation is fairly straightforward though. The first step, of course, is that we go through all the sets we have here, so through all the input values. We can do this with a for loop, and I can use a for of loop here to go through my input sets, so for set of sets. We can then do something on every set we got here. Now, what I want to do is, I want to take a look at that set and calculate the Cartesian product of that set with our temporary Cartesian product so that we slowly build up a complete Cartesian product. Put in other words, we'll follow a bottom-up approach where we gradually build up a bigger and bigger Cartesian product array in this function. For that, we can add a new variable, temp product, for example. And that initially will be the first element of that parameters array. So it will be the first argument initially, colors in my example here. And then inside of that for loop, we can call card product, so that function we wrote earlier, and pass in as a first argument temp product, which is an array. It's my first parameter here initially, and it'll soon be something else as well, but initially it's just the first array we're passing to Cartesian, colors in my example. And that will be the first set I pass to card product. And then the second set we pass to card product, that will be the set we have here in the loop. So now for the very first iteration of this loop, we'll feed our first element, colors, to card product, and the first element we have a look at from all the input arguments. Now the problem we would face with this approach is that, of course, here with for of, we go through all the elements in sets, so through all the arguments we received, and therefore, of course, we also again take that first set, which we already have stored in temp product though, and I don't want to multiply that first argument with itself. So therefore, I'll switch from a for of loop to a regular for loop where we have I, and I'll start with I equal to 1 so that I can start with the second element in that set's parameter, so in that array of arguments I received. And then I'll go as long as I is smaller than set's length, and I increment it by 1 after every iteration. So that's a pretty regular for loop. The special thing just is that I start with the element with index 1, which will be the second element. So that here I can simply access sets for index I, and that will be, well, 1, so index 1, so that will be the second element. So that for the very first execution of this function and of this loop, we call card product with the first element we received as an argument, so with the colors array, and with the second element we received as an argument, so in this example with the sizes array. Currently we're not doing anything with styles. Now card product will then give us back a new array. That's what we saw earlier, right? Product, which is returned here, is an array full of all those combinations of those two sets we received. So what we get back here is an array full of those combination arrays. And I'll simply store that back in temp product. So temp product initially is the first set we received, but after the first loop iteration, it will no longer be that. Instead, it will be our first derived Cartesian product for the first and the second set we received as inputs. After the first loop iteration, it is that derived Cartesian product array, and we'll then take this new derived array and combine that with the next set in line, so with the next input set we received for index 2 in the second iteration here. And that's that bottom-up approach, where we first build a small Cartesian product for the first two input sets, and then we take this small Cartesian product and combine that with the next set in line. And then, if we had more input sets, we would take this new Cartesian product and combine that again with the next set in line. And with that, we use a bottom-up approach to build up that overall Cartesian product. Well, and then in the end here, I can just return temp product because that will be my final result in the end here. And this actually should be all. We can now console log the result of calling Cartesian with those three sets. And if we do that, and I reload, you see we get an array full of 16 elements. And that makes sense because we have 2 elements here, 4 elements here, and 2 elements here. So we have 2 times 4 times 2 combinations, and that is 16. And if we expand this, you see we got a bunch of arrays in there. However, what you see is that the arrays look a bit strange. We always have round neck or v-neck as a last element, but the first element is another nested array. And I don't want that. I want a flat array in there. Put in other words, what's in the nested array here, blue and S, should be in the main array for that first element. So I don't want that extra nested array. Now we do of course get this extra nested array because when we build our temporary Cartesian product, that is an array full of arrays, and we feed this as our input to the card product function. Now in there we therefore get this array full of arrays, and we combine every element there with another element from the second set, from sets I here. Now since I feed in an array full of arrays, set AL will itself be an array. And that's why we create a new array where the first element already is an array and the second element is not an array. And that's why we have an array combined with something like round neck and v-neck here. Now to work around this, what we can do is we can go here and use the spread operator in front of set AL to make sure that we take all the elements from that array and add them as individual elements in that new array we're creating here. That kind of flattens this array and takes the nested elements out of it and moves them into the main array we're generating here. This approach, however, will cause us a problem with the first two sets, sets 0 and sets 1, where the first set is then just an array of strings or of numbers or of anything else, so where it's not an array of arrays necessarily. Then using the spread operator might not fail or do something unintended in the case of strings. To work around that, I'll add an extra if check here in the outer for-of loop, where I check if the element we have in the first set is an array. If it is not an array, hence the exclamation mark, then I want to turn it in 1. So that the spread operator always works, because it needs an array, so I'll turn the first element into an array if it's not one already. We can do this by overriding set AL with a new array, which simply includes set AL. So if it wasn't an array yet, it will now be one. And of course, in order to be able to override this, we should turn this from a const to a let, so to a regular variable. And now with that, if we try this again, we still have 16 elements, but now if we expand this, we see we have no nested arrays, but we have a flat structure, where we have blue S round neck, blue S V neck, blue M round neck, and so on. So where we have all those combinations. And this approach would not just work for 3 sets now, but for any amount of sets. So this would be a more generic version of this Cartesian product algorithm, which works with multiple sets. And the only thing we did here is we took advantage of this existing array, fine-tuned it slightly to work with nested arrays too, and then made sure that we go through all the input elements we might get in a for loop and call our original function for only 2 sets at a time. And this adjustment to work with nested arrays and to flatten them was needed because we do create that temporary Cartesian product here, which will be an array full of arrays, and that's one level of nesting too much, which is why we're using the spread operator here in our main card product function. Now for the time complexity. Previously I said that we had big O of n times m, but that we could generalize this to quadratic time if we say we only want to look at the length of one of the 2 input sets. Now I mentioned this possible generalization because we need that generalization here if we have an unlimited amount of sets. Because now, theoretically of course, the time complexity and the space complexity as well would be n times m times q times l times whatever you want for as many input sets as you have. But this is not how you want to express this, because you don't know with how many input values your algorithm is going to be called. For 2 input values, as we had it before, it was clear that you had, well, two values. But now you can't assume how many sets will be passed in. So we can't express it like this as a product of all these set lengths. We need a more general way of expressing it instead. That's why we have the big O notation in the first place. So it would be nice if we could express this in a more general way, and therefore we'll take this generalization I mentioned in the last lecture. We assume that the length of the longest array is the length of all the input arrays. That might not be the case, but this is the worst case approximation we can make here. So let's say this length is n. So we would have n, but of course that's not all. The length of the arrays is not all we have. Instead, it also matters how many arrays we have. Because before, with the two sets, where we knew that it always were two sets, we had n times m as the big O notation, or the more generalized form, on squared. Now we had squared here as this worst case generalization, because we knew that we had two sets, because it was in the end n times n, right? The length of the first set times the length of the second set. And if we had three sets, and we knew that it always were three sets which we got, we would have n times n times n. And that, of course, is just cubic notation, cubic time complexity, so n at the power of 3. And therefore, if we don't know the number of arrays in advance, we of course can know that it should be n at the power of x when it comes to the time complexity, where x is the number of input arrays. Because before, the power was the number of arrays. We had O of n squared for 2 sets, and n at the power of 3 for 3 sets. So the more general form is n at the power of x, where x is the amount of input sets we're getting, in this case 3. And n is then our worst case length, so the length of the longest set. And that's the same here for the space complexity. So what this essentially means, for the time complexity especially, is that if we now have 3 arrays as an input, we would have 3 as a value for x, and we would then take the length of the longest array, in this case this one here, 4, and that would be our value for n. So we would have 4 at the power of 3 execution steps, which we would assume. Now in reality, we will probably have less steps, because not all arrays have a length of 4, but again, that's our worst case generalization. And therefore, the Cartesian product has a general time complexity of n at the power of x for an unlimited amount of input arrays with any length of your choice. Now that we had our introduction to sets and set algorithms, let's move on to a very common form of sets and a very popular kind of algorithm you might be asked for in an interview, or which you should be able to solve logically. And that would be an algorithm about permutations, with and without repetition. Okay, what are permutations? What can we do with those? Permutations in the end are just ordered combinations of values. And they come in 2 flavors, without and with repetition. Now, this will become much clearer if I give you some concrete examples, of course. We, for example, talk about permutations without repetition if we have a look at to-do list items. Let's say you know that you have 3 tasks which you need to solve today. You need to walk the dog, you need to clean the toilet, and you need to order some food. Now, these are your 3 tasks for the day. Now, maybe you already have a clear order in which they need to be done, but technically there are a bunch of possible combinations. You can first walk the dog, then clean the toilet, and then order food. Or you first clean the toilet, then you walk the dog, and then you order food. Or maybe you want to walk the dog, order food, and clean the toilet, and so on. So you got multiple combinations here, but important, every task is only done once. That's why it's without repetition. Now, an example for a permutation with repetition would be the combination for your save, which you want to set. So for your save with all your valuable stuff in there. Now, let's say you have a keypad with only 3 numbers available, because it's a very insecure save. No matter, I just used 3 numbers to keep this simple. In reality, you would of course have 10 digits available on a keypad. So now you can program a combination. Now let's say the combination always must be 3 characters long, 3 digits long, but you are allowed to repeat digits. So you could therefore have a combination of 119, 111, 959, and so on. So you're limited when it comes to the length, but you can repeat values, and the order is also up to you. And that's why we're talking about ordered combinations of values. Of course, between the separate combinations, the orders can be different, but it is the order of items that sets those combinations apart. We don't just care about the values that are part of the array, we also care about the order of those values. And 2 combinations with different orders are treated as 2 separate solutions, 2 separate sets. So that would be permutations with and without repetition. Now, a common question in an interview could be that you, for example, get those 3 to-do list items, and you should write an algorithm that spits out all possible combinations of those items with or without repetition. Now, let's see how such an algorithm could look like and how we could derive it before we then, of course, also judge the time complexities. Now here I'll get started with the without repetitions scenario, so that we come up with an algorithm that takes some input and then gives us all possible combinations where no element is repeated. So for example, I have my to-do list items, and that is walk the dog, clean the toilet, and that should of course not be console but const. So clean the toilet, buy groceries, and order food. So I have 4 items here in one array, and this is the input which I want to feed to a function. Get permutations could be the name of the function, and I want to be able to call get permutations and feed in my to-do list items, and as a result I get all possible combinations in one array, for example. So I then console log that result array. That's the goal. Now get permutations therefore of course should take our array of input values as an argument. Now that's of course just one way of writing this function. You could also use the rest parameter to take a bunch of comma-separated input values, a bunch of comma-separated parameters, but I expect one parameter which should be an array with all the values which then should be used in the different permutations. So the name is up to you. I'll name this options, because this is an array full of our permutation options. We are free to combine them in different ways, and that's why I named this options. So what can we now do inside of this algorithm? Well, we want to derive all possible combinations, or as we call them, permutations. So I'll add a new helper variable, permutations, which initially probably is an empty array. And in the end, we'll return that array. But in the end, of course, it shouldn't be empty anymore, but instead it should contain a bunch of nested arrays which describe our individual combinations we came up with. So it should be an array full of arrays where every array looks like this input array, but where the items are then ordered differently, so that we have all possible combinations and orders we can come up with for those given inputs. That's the goal. Now what happens in between those 2 lines, therefore? Well, we probably need some for loop to go through all the options, right? We want to derive all possible combinations, so we certainly need to have a look at every option. So therefore, a loop probably makes sense, and I'll use a regular for loop where I start at the very first element, and then we go maybe through all options, and we increment I by 1 after every iteration step. So now we would go through all the elements, all the array elements we receive on the input array. Now every item here we got from that input array needs to be combined with all other items in all possible orders, in all possible ways of sorting those items, so to say. So that screams for a nested loop, but the problem here is we don't know how many nested loops we'll need, because we'll basically need one nested loop per extra element in the input array. Now this is a use case or a problem that screams for recursion, because with recursion we can call ourselves and we don't need to know in advance how often that will happen. We just need some exit condition that makes sure we don't call ourselves anymore if we got no more reason to call ourselves. That's how we could describe recursion. And recursion sounds like a fitting tool here since we don't know in advance how many nested loops we would need. Now, how can we use recursion here to solve this permutations problem? I'll say right away, it'll be a bit tricky to wrap your head around this, which is why after we wrote this algorithm, I'll also dump in some console log statements so that we can see what happens after we got the result. But to understand what we're going to build, here's the general idea. We got our input array of the different options we have. So of our to-do items, or simplified of A, B, C, and D. That's the input array we get on our main function call. Now, the idea with recursion, or of solving this recursively, is in the end that we call this same function again with a shorter array, where we omit the first element. So where we then just pass an array with B, C, and D into ourselves. And we'll do this recursively until, which we have to check with some if condition, until we only get one element. So until we get an array with just one element, then we'll not call ourselves again. Instead, we will then basically write some code to combine this single element with the other element we left out when we created that single element array. So we in the end combine D with C here. And with combine, I mean that we'll need some code, some loop, in the end, that gives us all possible combinations of these two elements. So C and D and C in this case here. Now, by splitting this problem into smaller arrays, we will be able to use a loop because we'll have simplified the problem. Because when we now derive these combinations, we'll combine these permutations with the element we left out to derive that middle shorter array. So in this case, we would combine B with CD and DC. And we'll derive all new combinations we get by combining CD and DC with B. So we'll get these combinations. And we would then take those and combine them with the last remaining element, A, in this example. So that's the general idea. And by using recursion and splitting the problem into smaller arrays, we'll be able to step-by-step build up those combinations. So we'll not have to compare everything with everything, which would require a huge amount of nested loops, and we wouldn't even know how many loops we need. Instead of combining everything with everything, we'll instead just combine one set of existing permutations, which we build up from the ground, with one extra element, so that we always just combine one element with a set of permutations instead of all elements with all other elements. That's the general idea. So here we could add a helper constant, partial permutations, for example, where I call get permutations again, so where I call myself recursively, and I feed in my options, but with the slice method and an argument of one fed to slice. This is the starting point of slice essentially, and slice, as you learn, takes a slice, a part of that array on which you call it. So this will then start at the element at index 1, so at the second element, including that element, and go all the way to the end of the array. So put in other words, it will take all the elements we have in options except for the first element. And then this new array, which is that options array without the first element, will be fed back into get permutations. And there we then call ourselves again, leaving out the new first element we have. And therefore, the array we feed to get permutations, to our nested recursive calls, will get smaller and smaller until there ultimately is just one element included. Now, of course, since we have recursion, we also need some exit condition, which we need to run before we call ourselves again. Otherwise, we would have an infinite loop. And here we should check if our length is equal to 1, which means we now have an array as an argument which just has one element. In that case, I'm fine, and I then want to return a new array that includes my options. So options already is an array with just one element in there. And I now wrap this in a new array so that we return an array with just one array, which then has just one item. That's what I return here. Now, why am I doing that? Well, because get permutations returns an array. We always return an array here in the end. And therefore, we should also return an array when we have just one element in our options array. Now, you could argue that options is already an array, but keep in mind that permutations, which we're going to return in the end, will also be an array full of arrays, because every permutation, so every combination of items, will be in an array, and all those combination arrays will be part of that overall permutations array. So we will return an array of arrays here too, and therefore that should also be the case here in our exit condition for the recursion. We should also return an array of arrays here, and we do. We now have an array full of options, which in this case is again just one array with one element, but still it's an array of arrays. That's the logic here. So now we have this exit condition, and with this step here, we therefore split our array until we only have an array with just one element. Now, partial permutations, therefore, when we drill down really deeply here in the recursion, will at some point only be one array with one array inside, which then just contains one option. Let's say which just contains order food. This at some point will be the case for some deeply nested recursive function call. So now we have our partial permutations. For example, an array with just one element in there. And now we want to find combinations of basically this item here with the other option we have here. Now, options is two items, for example, right? Could be buy groceries and order food if we're in some nested recursive calls. And we want to see how we can combine these two items, order food and buy groceries. Now, here we're going through all the options, and that's wrong because order food, one of the two options we have in this example case here, is already in the partial permutations. So I certainly don't want to go through all options again. Instead, what I want to do is I want to only go, for example, through all my partial permutations and combine that with the remaining options I have here. So with the options that are not already part of the partial permutations. So therefore here, I go through all partial permutations by using the length of partial permutations as my loop condition. And we can then derive our partial permutation, so singular, by accessing partial permutations for I. Now what this will do is it will go through all the permutations we have here in partial permutations. And in this example, there only is one, but of course you're not limited to one. The more recursive calls that have finished executing, the longer this array will get. So we go through all the permutations we derived thus far. And then I have a look at each partial permutation we have in there. And now we need another nested loop where we go through all the items in that partial permutation. And we know that we only need one more nested loop because each partial permutation will not have any other nested arrays. So here, for example, with just one element in there, we execute this loop once, and we have a look at the partial permutation we find in there, so at this nested array. And now I need access to the concrete items in that array, which is why we need another nested array. So here I'll use j as a variable, and we also start at the very first element, and we go through all the partial permutation, singular, items. Partial permutation is still an array, so we can call length on that and increment j after every iteration. So now with that, we have a look at all these concrete elements in that nested array And we want to combine that concrete element, or all those concrete elements, with the remaining option we got here. Now, we only have one remaining option at all times because we always slice after the first option here. So it's only that first option which we didn't slice, which we need to compare to our other permutations. So therefore, after slicing, before we enter any loop, I'll have my first option, and that is simply options for index 0. So that first option, which is not part of the array we fed to get permutations. And now it's this first option which we need to combine with our permutations. So basically, we just need a way of moving that first option in front and after our nested values. And for that, in this inner loop, we can derive our permutation in front, for example, and derive that by taking our partial permutation. So for example, this first permutation we have here. And then by slicing this to just take a part of that and slicing it from the beginning all the way up to j. So this index we have here. And we also have permutation after, or however you want to name it, where we do the opposite, where we take the partial permutation without an s at the end and slice it from j to the end. So we essentially just take that partial permutation we have here, which of course can have more than one element. If it just has one, there is not much to slice. But if it has more than one element, and we basically take different slices from that first permutation. For the first run, the permutation in front just has the first item. For the next run, it has two items, and so on. And we insert first option after those different slices, so that we basically inject first option in all possible positions in that permutation we already have. And that's what we do last here in this nested loop. We take our permutations, so that helper array we defined at the beginning, and we push a new permutation into it. And that should be an array, of course. And for that, we use permutation in front, which is an array because we used slice. Slice returns an array. And on that, we can call concat. Concat is a bit like push, but it takes arrays as an input instead of individual elements. And it will then merge those arrays with the array on which you call it. It will also return a brand new array thereafter. And to concat, we pass the first option. However, I just said that it operates on arrays, and the first option is something like buy groceries, which is a string. So we should wrap this into an array. And we pass another value to concat, and that is permutation after. And whilst this might sound, or it might look very complex, this will in the end move first option into all the different places in the different permutations we have. And we'll build up those permutations step by step with these recursive steps that we call. And then in the end, we return permutations. And that should be all. Now, I know that's super hard to wrap your head around. So let's first of all see if this works before we again take another look at it. So let's save everything and go back to the browser and reload. And what you see is I get an array here, an array with 6 elements. We have walk the dog, clean the toilet, buy groceries, and order food. We have clean the toilet, walk the dog, buy groceries, order food, and so on. So we get a bunch of combinations here. However, I can already tell that there are combinations I'm missing. For example, order food as a first element doesn't exist here. And the reason for this is a tiny mistake I have here in the for loop. This exit condition here, or this loop condition, is wrong. I go through all my j's as long as j is smaller than the partial permutation length. Now, as a result, if my partial permutation, like in this case here, is just one element, this array has just order food as a single element, this loop here will only execute once. Now, the problem with that is that I then take the slice here, and from 0 to j, where j is 0 in the first loop iteration, which is the only loop iteration we have, as I just explained, then slice will not include the element at index 1, so this will be an empty array. And this will be the other array. Now the problem is I need to go through that twice though, so that I add order food both in front and after the other element I'm comparing it to. So therefore we should have smaller or equal than here as an exit condition, and not just smaller than. And if we do that and we then reload here, now we have 24 items, and this looks much better. And if we go through that, It looks pretty good, I'd say. We should have all possible combinations here. And as you can see, we have quite a few combinations. We have 24 possible combinations for only 4 input values. So that's quite a bit. But this is now the permutation algorithm. However, I am aware that this is an algorithm which can be very hard to come up with and to understand if you haven't seen it before and if you don't know permutations from math or from anything else. So let's throw in some console logs to get a better understanding for this algorithm. So what's happening here? Let's add a console log here at the very start, fn start maybe for function start, and a console log options here so that we see what we actually got here as options. I'll also add a console log here after we called ourselves recursively, after recursive step, and there I console log the partial permutations so that we see what we got back from calling ourselves. And then here I will also log the first option. So let's console log that. And yes, we could use breakpoints too if you wanted to. And let's also console log in the outer loop here, outer loop, and console log our partial permutation, so singular without a s here, to see what's in there, here in this constant. And we could log here as well, but since we fill our final permutations here, which is what we return, that is in the end what we printed here, or what we received here as partial permutations from calling ourselves. So this should be fine, and if we now reload, we see a bunch of output there. So let's go through that. We start the function, and initially we receive all 4 options. It shouldn't be a surprise, because that's how we call ourselves the first time. Then we see another function start with only 3 items. This makes sense because very early in this function we do call ourselves again, and we sliced to call ourselves with all options except for the first one, which is why here you only see clean the toilet, buy groceries and order food, and not walk the dog anymore. We then call ourselves again before any of the other code runs, because that's how recursion works. We call ourselves here, the rest of this function execution pauses basically, and this nested function execution starts, which is why we start again with 2 arguments and then with 1 argument, order food. That's what I explained in theory a few minutes ago. Now we don't call ourselves again, because now we called ourselves with an array with just 1 element, which triggers this condition, and we return this 1 element wrapped in another array, which is why after the recursive step for order food, we see an array with an array inside, which is that order food array. So that's what I explained. The first option is then buy groceries. That's that one option which was not included here in this nested array when we called it from this function execution where we received 2 options. So that's that other option. And now we're in the outer loop. We have that 1 permutation we have from the nested call, which is order food. And this loop now executes, and we derive all possible combinations of buy groceries and order food, and we return permutations in the end, which means we're done with another recursive step, which is why we see after recursive step again, and now we see the result of that step, which is an array with 2 arrays with 2 permutations, and that's the 2 combinations we have for buy groceries and order food. And now we continue in that call. The first option here is clean the toilet, because for that call, where we had 3 arguments, we had clean the toilet and buy groceries and order food. We already combined buy groceries and order food, so now we need to combine clean toilet with the permutations we have for buy groceries and ordering food. So that's what happens here. Clean the toilet is now our first option. We have the outer loop, and in the outer loop, the first permutation we have a look at is the one where we have buy groceries first and then order food. And the second permutation is, well, the opposite. And then we're done with combining clean the toilet with these 2 permutations, and we get back these combinations. Clean the toilet combined in all possible ways with these 2 permutations. Well, and then again, we have the last first option, which is walk the dog. And we combine that with our other derived permutations we have here. And that's how we ultimately get this end result. So this is how that works. Now, what's the time complexity of that? Maybe try deriving this on your own first. We'll do it together in the next lecture. So what could be the time complexity here? We can already tell that for a relatively short input array, which has only 4 elements, we get 24 combinations. Now let me add one more element, just one more element. Let's say do homework. And I save this, so now we have 5 elements here. If I now reload, you see now we already have 120 combinations. So this grows super fast. This is definitely not linear, it's definitely not quadratic, and it's also not even exponential, which would already be very fast. But this is even faster than exponential because we can see a pattern here. For 4 items, we had 24 combinations. For 5 items, we have 120. Now this is actual factorial time complexity. So here we have time complexity, which is O of n factorial. Because for 4 items, we had 4 times 3 times 2 times 1 combinations. So that is 24. For 5 items, we have 5 times 4 times 3 times 2 times 1 combinations. So that is 20 times 3, which is 60, times 2, which is 120. So we have factorial time complexity here. And factorial time complexity is horrible. Now, actually, there is no better alternative to this algorithm. Of course, you could come up with different code that produces the same result, but you won't find an algorithm that derives all those permutations with less than factorial time complexity. This really just is a bad time complexity. It is something you want to avoid. If you have to solve a problem like this, you might need to come up with some other improvements, some other ways of maybe shrinking the amount of inputs you have to deal with or anything like that, because if you have to derive all those combinations, you have factorial time complexity. And this will be slow. And if you add only a couple of more items, this will crash your browser and maybe also your entire machine. So handle this with caution. Now, you might be wondering, why is this factorial time complexity if we just have that many combinations? Well, because every combination has to be generated in our code, right? And in the end, we generate our combinations here in this for loop here. That's where we in the end push a new permutation onto our permutations array. The fact that we have recursion here doesn't matter too much, because in the end that is just like an extra loop step. It just leads to this entire code being executed one more time. So therefore we have a direct dependency on n, and we can simply count the number of combinations that we build in the end here, because this is our most deeply nested code that we have inside of the for loop, inside of a for loop, inside of a function that calls itself. So this code is definitely the line of code that is getting executed most often. And that's the line of code we have to measure to find out our overall time complexity here, of course. And therefore, since this runs for every combination that is generated, the number of combinations that is being generated gives us a clear idea of our time complexity, because we need to run this line of code once per combination. So now that we had a look at permutations without repetition, let's now have a look at permutations with repetition. How does this look like? Now for that, I'll come back to that save, to that password example, where we have, let's say, our digits. Let's say 1, 2, and 3 are the digits that are available to us. And we have a certain result length that is required. Let's say we want a code that consists of 3 digits. And we then want a function that generates us all possible combinations where, and that's the difference, every element of digits can be used more than once. That's also why we have to define a result length, because otherwise it would not be clear which length the result array should have. Because previously, of course, if every item could only be used once, there is a finite amount of combinations. If you can reuse items, there is no finite amount of combinations. You need to instead set a length that shouldn't be exceeded. Otherwise, you can, well, generate a combination of this length of just once, right? So that's why we now need this extra input. And then we can get our functions, get permutations, which now takes two inputs, our options, but also our length. And that's important. We get the length from external now, so as an input, because, as I just explained, we can't derive it from the length of the input array. So the goal is again that I can call get permutations and pass both my digits as well as my result length to this call. And now in here, we should, in the end, generate all those possible combinations. Now, the general approach is the same as before. We will split this up into smaller problems to basically just derive combinations of length 1, and then combine those 1-element combinations with one extra digit to derive all possible 2-element combinations. And then we'll again combine all those possible 2-element combinations with the last element, so that we again don't have to combine everything with everything right from the start, but we start instead with simple arrays, and we then gradually add more and more combinations to those already combined arrays. So therefore here, in that function, at some point, we will again call ourselves and store that in our partial permutation. So same logic as before. But now we don't call ourselves by slicing options. Instead, options will now always be the same array, but will reduce length by 1 here. So our input length, which initially in this case here is 3, will only be 2 for the first time we call get permutations in that main function call. And then we also need some exit condition to avoid an infinite loop, where I check if length is maybe equal to 1. And at some point it will be 1 because we continuously decrease length here. So we will reach length 1 at some point of time. And if we have a length of 1, I again want to return an array with all the combinations of length 1 we can come up with. Because just as before, the overall goal of get permutations will be to derive an array full of all those permutation arrays we can get. So an array full of arrays. That's what we will in the end still return here inside of this function. So at the end here, we'll return permutations. And since we return an array full of arrays here, we also need to return an array full of arrays here in this exit condition, so that we return the same kind of data. Because get permutations is a function that always should return an array full of arrays. Now we could return options, but that's not an array full of arrays, that's an array full of numbers. And it's always the same array of numbers because we never slice it or anything like that. So that's a major difference to the other permutations algorithm we had. But what we want to return here is in the end all possible combinations where every permutation only has a length of 1. Now of course that in the end means the array I want to return here for this input example should be an array full of arrays where we have an array with 1, an array with 2, and an array with 3 as a child, so as a nested array. So that's our main array, and the individual arrays are just, well, arrays that contain those individual elements wrapped into arrays though. That's the goal here for a length of 1. Because for those options, these are the 3 different combinations we can come up with if we have a length of 1 per combination. Now, of course, I don't want to hard code it like this though, because I don't know which digits or which options I'll get. So instead, we can use options and use the map method on that to map every option into an array. So to simply wrap every option into an array, and map overall then returns an array, and therefore that's an array full of arrays, which overall is returned in the case of length 1. That's the logic here. So partial permutations will always be an array full of arrays, and those arrays in the array will be the possible combinations for those given options and the given length. Now, of course, we don't just want to have an array with single elements wrapped into an array. Instead, that will be our, well, most deeply nested recursive function call. So in the most deeply nested recursive function call, we will get back an array that looks like this here, what I just basically outlined. So an array with 3 elements, where every element is an array with just 1 element per nested array. And now we need to combine those single digit, those length of 1 arrays, with all other options again. So therefore now here we can again add a for loop. And now, since repetition is allowed and wanted, we can simply use a regular for loop where we go through all options. So for option of options, we go through all the options we have here. And we go through all the existing permutations which we derive from the nested function call. So another nested loop which is needed here. And that's our existing permutation of partial permutations. And we'll now simply take our main permutations, so the overall array which we're working on, and we push a new item onto it, and that should be an array as you learned. And that new item, which we want to push here in the end, should be our existing option here, which is not an array though, but a single item, because options is the options we receive here. That will always be an array of individual elements. So option is just such an individual element. And I rather want to push an array instead of a single element. So I'll wrap option into square brackets so that we have an array. And we concat our existing permutation to that option. And this in the end will combine every option with every existing permutation. And we do this here for all possible combinations. And then we return this in the end. And this will therefore gradually build up all permutations. So if we save this and reload, we see 27 results here in this case. And if I expand this, we see 111, 112, 113, 121, and so on. And this looks pretty good to me. We got a bunch of nice combinations here. And you see there are a lot of combinations for just 3 digits. That's, by the way, why longer passwords are more secure. Because if you have short passwords, computers, like our script here, can relatively easy combine all possible combinations and simply try all those combinations in the password field of some website, let's say. Now, the longer a password is, the longer it takes to generate all possible combinations, and you'll quickly reach a point where no modern computer is realistically able to do that. So therefore, longer passwords are safer because, as you see, combinations grow quickly. We already have a lot of combinations for just 3 digits. And indeed, if I add a 4th digit here, so just 1 extra number, you see instead of 27, we now have 64 combinations. So this really grows extremely fast. Now, as before, you can dump in some console log statements to understand how this works. Since the logic is very close to the logic we had before, with the adjustments made, which I explained, I'll not do it here, but definitely feel free to do that if you're not sure how this algorithm works exactly. Instead of doing that, I right away want to focus on the time complexity instead. What is the time complexity of this algorithm where we do have repetition? Do you have an idea? Well, before we had factorial time complexity, and that was without repetition. Now, with repetition, we got more possible combinations than before, so we probably are not doing better than factorial time complexity. And indeed, we don't. If I add my time complexity here, it actually depends on 2 input factors. Because we're feeding in an array of elements and also a certain length that we want to have for the combinations that are generated. And both impacts how often our code executes. If we pass in a longer array, we have more digits we have to go through. If we want a longer combination, we have more combinations that we need to generate. So both these factors have a very important and a very strong impact on the time complexity and on the number of execution steps we have here. Well, in the end, we can just count again, and we can count our combinations. Because just as before, every combination needs to be produced, and therefore the number of combinations tells us which time complexity we have. And we saw that from 3 to 4 digits, we had a pretty steep increase. The same would be true if I increase the length we want to generate by just 1, from 3 to 4. If I do that, you see we have 256 elements here. So that is what I meant with the password. If you just want a password that is 1 element longer, you got way more combinations that can be generated. So both inputs have a strong impact. And indeed, the time complexity here, therefore, is n at the power of r, where n is the number of options and r is the number of slots, so is the length, so to say. So here we had 4 at the power of 4 if we would want to fill out those blanks. So n at the power of r, number of options at the power of the wanted length, that's our time complexity. And this grows super fast, as you can tell. If I just bump this up to 6, you see we already jumped from 256 to 4096, and that's a huge increase. And you can quickly reach areas where your script will just freeze. Now, of course, it's nice that I tell you that this is the time complexity here, but how can you derive this on your own? Because that's something I didn't do here with you. Well, let's have a look. N at the power of r. We know, for example, that we typically have quadratic time, so n at the power of 2, if we have a nested for loop and we go through all the elements of one array in those nested loops. Well, we do have nested for loops here, but of course we also have some recursion here. And that's really important, we get 2 input elements. So we certainly can't have a time complexity that just depends on just one element, because clearly both inputs have a strong impact on the time this algorithm takes. Even if you don't know this in advance, you can easily tell that both inputs have a strong impact if you have a look at the number of combinations you got and how fast this number grows, no matter which of the two you manipulate. So that's a clear indicator that our time complexity needs to depend on 2 variables and not just 1. Now, why n at the power of r though? Now, to find out how these two are related, you can simply simplify your inputs. And for example, say you have a length of 2 and you have 2 digits. And if you do that and you reload, you see 4. So 4 combinations. Now let's increase the amount of digits, but keep the length unchanged. So we have 3 digits, but still a length of 2. If we do that, you see we grow from 4 to 9 combinations. Okay, so let's now change this to 4 digits and still keep the length. So 4 digits, length 2. And we got 16. So this looks very quadratic to me, because 3 at the power of 2 is 9, 4 at the power of 2 is 16, and 2 at the power of 2 is 4, which we saw earlier. So it looks like this, the number of elements here at the power of length, is our time complexity. And just to verify this, let's increase the length here to 3, from 2 to 3, and go back to just 2 digits. If I do this, we now got 8. So our theory still seems to be true, because 2 times 2 times 2 is 8, and that is 2 at the power of 3. So it looks like we have n at the power of r. Let's verify this by adding 1 extra digit, so that we have 3 digits here. And if our theory holds, we should now have 3 at the power of 3 combinations, which would be 27. So if I reload, yep, we got 27 here. So that looks good to me, and that is how you can derive this on your own. You can simply count combinations and then quickly find out what impacts the number of combinations in which way.